important phenomenon based on refraction that takes place in the atmosphere, which is known as atmospheric refraction. The optical medium here is going to be air. The first important phenomenon is apparent position of the stars. That is, whenever we observe the stars, we do not see their actual position in the sky. What we see is the apparent position, which is slightly higher. We shall consider whole of the atmosphere to be divided into different layers of air of varying densities. So assume that whole of the sky or whole of the atmosphere is divided into different layers, and all these layers of air have different densities, with the topmost layer having the lowest density because it is warm air. Warm air always rises up. So the topmost layer is going to have low density, while the bottommost layer is going to have high density. Now we imagine a star in the sky, star high up in the horizon, whose starlight we are considering. So somewhere here we have the star, and we want to observe what happens to its starlight when it is coming towards us. So a ray of light from the star is traveling to the first interface of air. It shall go from lower density to higher density, and hence it is bending towards the north, slightly bending towards the north. Again, at the second interface, it is traveling from low density to high density. Again, it will bend towards the north, slightly bending towards the north. Again, at the next interface, it is going from low density to high density. It shall travel towards the normal, bend towards the normal, and hence. So this keeps on happening till the ray of light reaches our eyes. So somewhere here we are standing and we are observing at the star with our eyes. Now our eyes have a limitation that we cannot see in a curved path. You can see that the starlight is coming in the form of a curve. We can clearly see that it is not following a straight line path till our eyes. It is coming in the form of a curve. Our eyes cannot follow a curve. So when our eyes retrace the path, it sees that the star is somewhere here high in the horizon. Our eyes will always follow a straight line of sight. So we think that the star is somewhere here, which is the apparent position of the star. Right? You can see that the position of the star has shifted for us when we are observing from the lowest level on the ground. That new position of the star is its apparent position. It is not its actual position. What happened was the starlight was traveling through different densities of air. While passing through different densities of air, it continuously keeps on bending towards the normal, due to which the path of the light becomes curved. But due to the limitation of our eye, we are not able to follow a curved path. When our eye retraces the path along our line of sight, which is always a straight line path, we observe that the star is somewhere higher in the horizon. That position of the star is known as its apparent position. The second phenomenon that we have mentioned here is about twinkling of stars. Now that is also related to the same thing, that different layers of air have different densities. Air never remains steady. It keeps on moving. So all these layers of air keep on mixing with each other. They keep on intermingling with each other. Now what happens due to intermingling is this star, that is the apparent position of the star, often goes out of sight. Sometimes the star goes out of sight on this side. Sometimes the star goes out of sight on this side. And sometimes it comes exactly along the line of sight. So what happens is, it comes inside the line of sight, it goes out of line of sight. Again, it comes inside the line of sight, and this process continues due to movement of air of different densities, which gives us a feeling, which gives us a perception that the star is twinkling. Actually, the star is not twinkling. It is the air that is moving, air of different densities, layers of different densities are moving and intermingling, in making the star go out of line of sight. This gives us a perception that the stars are twinkling. Now, a big question, why do planets not twinkle? If stars are twinkling, then why are planets not twinkling? So, as compared to stars, planets are quite closer to us in the atmosphere. Not very, very close, but if we compare to the stars, stars are millions of light years away from us, while planets in the upper atmosphere are quite closer. In that case, the planet will never go out of line of sight for our eye. Now, since the planets never go out of line of sight, we never get the twinkling, right? So, three questions together. We can talk about apparent position of the stars. We can also explain how stars appear to twinkle, and we can explain why planets do not twinkle. The next reason that we are going to talk about, the next phenomenon that we are going to talk about is why does the sun appear to be bigger during sunrise and sunset? We have already studied that due to refraction, consider refraction in say water. So this was a phenomenon we had talked about last time when we put a pencil in water. So if you observe this at home by putting a pencil in water, you will observe that the pencil appears to be thicker. Similarly, the coin placed in water appears to be enlarged. You put a coin or a ball inside a glass beaker, you will find that these objects appear to be enlarged, they appear to be slightly bigger. It is for the same reason that sun appears to be bigger during sunrise and sunset. Sunlight is also suffering atmospheric refraction, either when the sun is in the west or it is in the east. That is when sunlight has to travel the longest distance in the atmosphere. Due to the traveling of the long distance in the atmosphere, there is a lot of refraction taking place. Now, when a lot of refraction takes place, the sun appears to be slightly bigger and slightly raised in the sky. So, suppose sunrise is going to happen at 6:30 in the morning, 6:30 a.m. That's we would be able to see the apparent image of the sun or apparent position of the sun 2 minutes before sunrise, that is at 6:28. The sun rises at 6:30, that is when we will see the sun actually. But its apparent image is visible 2 minutes before the sunrise. Same thing happens at sunset. If sunset timing is, suppose, say 7:30 p.m., that is in the evening, we shall be able to see the sun even after sunset for 2 more minutes, that is till 7:32. That is because we are looking at the apparent position of the sun. The sun has already set, but its apparent image, which is slightly higher in the sky, slightly above the horizon, is still visible to us for 2 minutes. This phenomenon, this atmospheric refraction of sunlight, increases the length of the day by 4 minutes. 2 minutes before the sunrise, 2 minutes after the sunset. In short, the length of the day appears to have increased by 4 minutes. That is also due to atmospheric refraction. Another important phenomenon is during a campfire. The face of a person sitting opposite to you in a campfire appears to shimmer. It appears to be glittery. Now we know that campfire happens mostly in winter seasons. So when they burn the wood, the air above the wood is quite hot. That means its density is less, while all the other air surrounding the campfire is cold. And again, the air never remains steady. It keeps on intermingling. The different densities of air keep on intermingling. And the fire light keeps on moving through these different densities of air, due to which refraction takes place again and again, and we get a perception that the face of the person sitting opposite to you is glittering or it is slightly shimmery. So all these phenomena are based basically on atmospheric refraction, wherein the refraction of light is taking place through air of different densities. And we are supposed to remember that the lowest density air is at the top, while the highest density air is at the bottom. Next phenomenon. If we have a thick glass plate or a mirror, as shown in the diagram, we have a thick glass plate. It is not a simple mirror, which is a very thin mirror. It is a thick mirror. Now, since this mirror has a certain amount of thickness, it becomes an optical medium through which refraction can take place. So, if we look at what is happening here, we can see that if a ray of light is coming from an object A, it hits the point C. At point C, two phenomena are happening. Some amount of light is reflected towards H, and the remaining amount of light is transmitted through the glass plate, since it is a thick glass plate. Now, this glass plate is polished from the other side, so it is a mirror as well. At point D, the ray of light is reflected towards E. At E again, two phenomena take place. A part of light is refracted out from denser to rarer medium. You can see it is bending away from the normal, and the remaining light is transmitted into the optical medium towards point F. Again, at point F, two phenomena take place. Just one phenomenon, reflection of light from the painted portion. At G, two phenomena take place. Refraction takes place because the ray of light is going from denser to rarer medium, and a part of light is transmitted inside. If we keep following this process, we get multiple images formed behind this mirror. We can see here, if we extend these lines backwards, exactly in the line of the ray that is going out, if I extend this backward, I get the first image at A1. If I extend the second ray backward, we get the second image at A2. If we extend the third ray backward, we get the third image formed at A3, and so on. We can get 6 to 7 images in this particular thick glass mirror. You can get multiple images depending upon the length of this glass mirror, right? The diagram is important. Also, why do we get multiple images? Because multiple reflections and refractions take place in this mirror, which form many images. An important point to consider is that image A2 that is formed is the brightest image here. Image A2 is the brightest image out of all the images formed. Why so? Out of all the images formed, A2 is the brightest image, since maximum reflection and refraction takes place here.